All right, everybody. I hope you can hear me. Okay, so today I came to speak a little bit about my research project that I was doing this year, basically, and it related to hardware acceleration of Suricata. A little bit about myself. I'm Lukas. I'm OISF core team member, and in there I'm the DPDK maintainer there, aside from other side tasks, and I'm a researcher at CESNet, which is Czech NREN, which helps me to proceed with my PhD. Essentially, I'm interested in system design, making packets go faster, and general optimizations. You have also socials if you want to join me. All right, before we begin, I just wanted to maybe remind the Suricata architecture, which has 4 main modules. In the first packet acquisition, we receive packets. Then we do some, let's say, housekeeping, decoding, stream reassembly, and so on. So we prepare the packet and flow and stream for detection. And then we have some rule set of signatures in the detect module, which is the juicy part of Suricata. And then we go into outputs and we report what we found and decode it. What was the basically goal of the research project that we started with Suricata? It was just to mainly accelerate Suricata in general, because as you know, network links are getting faster and faster, and we need to keep up also from the software side as well. We took, let's say, university traffic, and we captured it, used the general rule set, ET open, and made a, let's say, a flame graph where we divided individual parts of Suricata and where the time is spent for Suricata. And we can see the packet acquisition is still taking quite a bit of time. It's around 17%. The decode and stream reassembly takes around 18%. But again, the detection, the most juiciest part, is taking the majority of the time, 56%. So that kind of gave us an idea. Like if you want to optimize something, the most impactful thing to optimize is, of course, the detection engine. And from the detection, at least for our trace and our setup, the packet payload prefilters turned out to be the most expensive part of the detection. Because it inspects basically every packet that goes into Suricata. Then Suricata inspects the reassembled stream as well, if required, and the amount of work just funnels down. The further you go into Suricata, the less packets Suricata actually inspects. So the deeper inspection in Suricata actually are pretty minor, like application layer protocols, meaning the sticky buffers, or the final detection where you really finalize the alert detection with other types of detection methods. And so we kind of focused on packet payload pre-filtering or pattern matching optimization in this work. This profiling graph, as you may know, might be different for different traffic, different rule set, different CPU, but this is, let's say, how it kind of turned out, and when we compared with other, let's say, papers, it kind of matches up. So So yeah, we decided to offload it to the hardware accelerator. The original plan was kind of easy. It was, let's say, a recently introduced card, NVIDIA Bluefield, that has a RegEx matching engine on the card itself. And so the idea was to use this engine and take the traffic that's received by the port, send the data through it, get metadata attached to the packet, and then send this thing to SuriCata so it can better decide whether it needs to go with the detection or not. So getting the card was, of course, easy. But soon enough, we ran into dozens of issues, of course. One of the main things is that, at least in this Bluefield card, the RegEx engine is just a Lukas side offload, meaning you cannot pass packets directly from the network port through the RegEx engine. You need to first receive data to CPU, and only then send data back to the Bluefield 2 and back for inspection. It has, let's say, hard to predict performance. The promised throughput of this RegEx matching engine was 40 gigs, but as we found out, it kind of varied in different environments, let's say, with a different number of rules. With different rules, it also may have varied. So those are kind of some of the things that we need to also a bit consider. And so the use of pattern matching metadata, as we thought might be a good idea, was not possible because yeah, we couldn't attach it directly to the packet. So here I have a quick intro to the card, how it looks like. So it's a data processing unit. In the hardware RegEx engine, it said that it supports 32,000 patterns. On the diagram, we can see that the network port is on the left side, and the data plane goes up to the ports, to the host. And from the host, you can only send packets back to the RegEx engine if you want to use it. Other specs of the card is a 100 gig card, supports DPDK RT-Flow, and has ARM. We considered ARM, but actually in the A72 cores are pretty, well, are not as performant as we were hoping for. So we just went and used the host CPU for this work. So this is basically what I talked to about the varying performance of the RegEx engine. To achieve a zero drop, let's say 35 gigs, we could only achieve it in this graphs under certain conditions. So the y-axis is the throughput, and the x-axis is the varying packet size. We loaded the RXP engine with 2,000 rules and observed the throughput. And what we've seen is that if the RegEx engine had the 2,000 rules and the packet size was over 1 kilobyte, then it was actually able to reach the 35 gigabits of throughput. But if you had lower packets, meaning you had more operations per second, then the throughput just dropped. It was kind of increasing line with the lower number of rules, but it got very much worse with the high number of rules. Let's say when you are close to 30,000 rules, your packet needs to be actually very big, so like jumbo frames, to be able to even reach the 35 gigs. So we were kind of skeptical if this project will lead to somewhere. It also something we had to consider, except the throughput issues, was the high latency. On average, latency when compared to hyperscan scanning could be even 5 times higher. But one thing that kind of kept us going was the asynchronous mode, and that's basically you can send buffers to the RegEx engine, to the Bluefield, let's say, and you can do something else in the meantime, and then later on you can pick them up, the results from your buffers, from your inspected buffers. So that's what we thought might be useful for Suricata. So how we proceeded and integrated RXP into Suricata. So what we thought, we can leverage the asynchronous architecture, meaning we will send buffers to the RegEx engine, and in the meantime, we will process other packets from the network port. Like we will just receive and decode the packets while we wait for the inspection results. We focused only on packet payload matching. That's from a number of reasons. The RegEx engine requires huge page memory, and luckily enough, the work has been based on DPDK, which works with huge page memory. The packets were already in there in huge pages, so we just took the packets, sent it to the RegEx engine, and we were done. We experimented also with the, let's say, stream reassembly pre-filters, but when copying was introduced, when we had to copy data from the, let's say, user space memory into huge page memory, it was just a performance killer, and that's why we went with packet payloads only. When we were designing this, we always had a fallback ready. Basically, when the RegEx engine didn't have enough throughput, it always falls back to Hyperscan as a fallback. And we use the host CPUs for the more performant alternative. So we proposed the synchronous model into Suricata. The left model is what we know how Suricata operates normally. Let's say the blue packet is received first by Suricata. So then it's fully processed, and it's completely outputted. Then the second packet in the third step is received by Suricata, and the fourth step is being completely outputted. While in the asynchronous model, it's a little bit different. The first step, the blue packet, is received. It's sent to RXP or to the Bluefield engine for inspection. But while we wait for the results, we receive the second packet in the third step, and we also send it to the Bluefield engine for inspection. Then we only collect the results from the inspection and finish the processing of packets. Okay, and here are some results. So this plot shows basically the scaling of the solution. So x-axis is number of threads, number of workers in Suricata, and the y-axis is the throughput. What we can see here is that one core, let's say in this case, is noted to reach 3 gigs, while the the dark blue, the async-Cata or the asynchronous SuriCata reached at least 8 or 7 gigs. Basically, what we can see, the proposed solution kind of scales well with the increasing number of cores. We can see a plateau from cores number 5 and so on, but that is caused because we hit the packet replay limit, so we need to fix this, and we will continue. The research is not yet over, so we will extend this plot. But basically, this plot shows that we continuously beat the SuriCata baseline version. Actually in this graph it shows the doubled performance. This needs to be very much confirmed if it is doubled, but we could see at least a 40% improvement. Maybe you remember the packet profiling graph, the flame graph in the beginning. And there was the packet payload pattern matching that took 35% of CPU time. So if we cut this part out of SuriCata, we would expect only 35% improvement at most. But the offload basically helped SuriCata to increase the performance even more. And we were kind of surprised, why is that? But after some inspection with perf, we came to conclusion, basically as SuriCata is inspecting less memory, it's causing less cache misses. Its memory footprint is overall lower, and that's why we were able to beat the 35% expected improvement. Here is the, let's say, on the left we have perf stat of the baseline version. It's probably a little low, but it says 16.8% of L1 decache misses, while the new version, there are only 5.4 L1 decache misses. So it also brings this little unexpected improvement as well. Some of the lessons learned from this research project, although it's not finished yet, so you should always test your equipment, even though the vendor might say fantastic things. Always do your testing. Then the RegEx engine can basically confirm that it's still useful to look at the hardware offloads and the software-hardware co-living, let's say, as it might result in nice results. And by reducing the memory footprint, we can optimize the application even more than what they actually take. Like the parts of applications that take, let's say, 30%, we can increase it even more if we reduce the memory footprint and stay within the cache area of the CPUs. And this basically shows that the asynchronous operation is possible. Like SuriCata could potentially also operate in asynchronous mode, although now it only operates into like synchronous pipeline mode. And how we would like to proceed further, so we will finish the measurements. Overall, of course, this architecture is not ideal to send data from the card over PCIe to CPU and then back to the RegEx engine. So what would be more ideal would be to have the hardware accelerator within the FPGA and then take the results immediately from there, considering we only focus on packet payloads. And with this, hopefully, we will get over 100 gigs on commodity, not super high-end servers with this. And this also opens up a question if there would be hardware accelerators which could do the, let's say, inference faster than on the CPU. We can also leverage this within Suricata. So the RegEx engine is just one example, but the work can inspire maybe others as well to use other accelerators as well within Suricata. Okay, so that's it from my side. Thank you.
Hi, Leo from Graphics again. Also, I guess, I don't know if my top favorite talk or second favorite talk, but that was great. I agree with what you're saying about the commodity hardware, and so actually what I was curious about was there are actually a lot of great, or not a lot, but there are CUDA-based RegEx engines, and I was curious if you had a chance to look at those, and then especially going to more commodity cards like T4s or V100s, and around those, I'm kind of curious about memory versus CUDA core count, kind of where you're seeing the pressure.
Right. Basically, no. I'm aware of the existence, but I didn't have a chance to try them out or, let's say, compare. I've seen them being very popular a few years back. I haven't seen such popular projects nowadays. I know that within Suricata there was already an effort to integrate the GPUs inside Suricata. It didn't quite work out, so I wanted to try a different path, and this RegEx accelerator already had an API ready, and it was kind of complete product. I didn't want to go into that field like, okay, let's implement the pattern matching engine on GPU now. So I wanted to use something pre-made for this.
Gotcha, thank you. And also, just on the, maybe helpful, on the, I also agree with what you're saying in the data path. We had really good success with GPU direct storage to skip the CPU, so going directly from SSD at 100 gigabytes per second to the GPU. SSD is obviously limited, so we needed a parallel storage array. But what I've been curious about, if I was going to go in this direction, is actually GPU direct networking for the exact reasons you're laying out. So again, really great talk, so thank you.
Yeah. Maybe I would highlight one technology. You mentioned CUDA, but cool kids now use Doka, which is the direct network to GPU networking. But that would probably require just transferring Suricata pipeline completely to the GPU, and yeah, this would be quite a bit of work. So.
Hello. Yeah.
Yeah.
Plus one to the guy. Great talk. I've also been testing DPDK and running on a couple different network cards, and recently, since thinking of scaling to 100 gigs, so close to buying about acquiring an NVIDIA card, but you are using Bluefield too. Is there something you thought about Bluefield versus ConnectX for 100 gig capacity, or?
Sorry, Bluefield versus ConnectX?
Yeah, is there?
No, basically we use the Bluefield just because of the RegEx engine being on the board. Otherwise, for general networking, I believe ConnectX is very much sufficient.
So it's not part of this RegEx engine, it's not part of the framework that's provided in the host, but it's on the card, you're saying?
Yes, it's directly on the card.
Okay, cool. Thanks.
I have a question in Discord, and what kind of drops have you considered in your analysis?
Sorry, what kind of drops?
Yeah, what kind of drops have you considered in your analysis? Maybe add more detail in the question?
Okay. In this measurement, it's supposed to be zero loss throughput, so that's the best throughput until the first drop.
In Discord, you can follow up with that question, and I think Lukas will probably answer you in Discord.
Okay.
One of the first slides that shows, that shows normal Suricata, synchronous Suricata operation.
This?
No. Probably next. This one, yeah. Так. It actually shows only one and single thread, worker thread behavior. Does it mean that RegEx offloader also has different threads, or some enqueuing and dequeuing exists from worker threads of Suricata to RegEx engine?
Yes. RegEx engine have as many queues as are configured on the network interface. So it was one-to-one mapping, one receive queue, one Suricata worker, and one RegEx queue, basically.
So the right picture shows, let's say, complete communication of one Suricata worker.
Yes, but you can have multiple threads or workers working simultaneously. You would just have more these arrows up and downs.
I understand, thank you.
And I think I need to mention this, that the RXP or the Bluefield engine does have the RegEx engine for Bluefield 2 and 3, but NVIDIA basically decided to go full AI and will be removing the RegEx engine in Bluefield 4, so it's kind of unfortunate, this reason.